All right, so today we'll be looking at relations, and we should be able to finish relations within the class time, and probably start to introduce you to what the real number stuff will be like. All right, a relation is, well, in math, a relation is generally something said between about two numbers, relating them to each other. For example, to say that 5 is greater than 2, that's a relation. That's a relationship between 5 and 2. The 5 is greater. You could say 6 is equal to 6. Relationship as well. We're going to give a general definition for it. So remember, we had, oh, excuse me. Sorry about that. All right, so remember we had, when we mentioned the cross product, A by A, let's say if you have two sets of numbers, natural numbers, and let's say the set in A, like this set is in A, of course it will be in the same A again. So if you had 2, 3 by 2, 3, well, you know what? Let me not do that one. Use two different numbers. So we have in A, we have these two sets. We have say 1, 2, and 4, 5. So if you were to use those two, 1, 2, oops, 1, 2 by 4, 5. Actually, the possibilities you can get 1, 5. You can get, sorry, 1, well, yeah, 1, 2 as well. 1, 2 is there already. But if you want to multiply others, you can get 1, 2, sorry, 1, 4, 1, 5. What's the next one? 2, 4, and 2, 5. Right. Good. So in this case, we have not specifically said that 1 is related to 2 or the 4 is related to the 5. But when you have set up a relation now, the result you get can actually be telling you what's happening between the two numbers. Let me show you what I mean. All right, so write this down first, and then explain more in detail. So here's a definition of a binary relation. Definition of a binary relation. And then I'm going to show you how it comes into what we were saying a while ago. So given a set A, oh, by the way, I think I said cross product, I mean Cartesian product right here. Cartesian product, not cross product. All right, back to what I was saying. Given a set A, a binary relation on A, a binary relation on A is a subset, fancy R, I don't know, write as fancy as I see it here. But generally when I was in class, I used to write like that. Maybe more like this. Yeah. Is a binary relation, sorry, a binary relation on A is a subset R, and it's a subset of the thing I was showing you a while ago, A by A. Which are those pairs where the relation is said to hold? Which are those pairs where the relation is said to hold? Full stop. So now, if, write this down, next sentence, if A, B write the words this time, don't write element of auto, write the actual word. If AB is in R, is in R, comma, I'm trying to paraphrase, understand. So if AB is in R, instead of writing AB element of R, so if AB is in R, comma, instead of writing AB element of R, we write A is related to B, ARB. So if AB is in R, instead of writing AB element of R, we write A is related to B. All right. So let me give an example of how what a relation would look like. So here's an example now. I'm going to clear the board. Let's say we have the set B, and this set contains, let's say, 1, 2, 3, and 4. All right. So let's use the relation less than. So let's use this relation using the less than relation. Less than right here. Here are the pairs that would be in the set R. If using the relation less than, the pairs that would be in our relation would be these. We would get 1, 2, because 1 is less than 2. You would get 1, 3, because 1 is less than 3. You'd also get 1, 4. 1 is less than 4. Also get 2, 3. You also get 2, 4. And finally, 3, 4. So that's using the relation less than. Because 1 is related to 2, because 1 is less than 2, 1 is less than 3, 1 is less than 4, and so forth. If you're using relation less than. Understanding? Hello? Well, I mean, yes.
Can you repeat what you just said?
About what? Because the last thing I said was, are you understanding? You talk about the R?
I don't understand the less than R thing. What does the less than relation have to do with the pairs?
Oh, when you're using the relation, you have to define what the relation is. The relation I'm using is less than, where we would say that the first number is less than the second number in the pairs. Because when you have a relation, if you say that R is related to B, this is what you're saying. You get the pair A, B. But you have to define what the relation is. In this case, I'm using the relation R to mean A less than B. So my R that I was using in this relation right here means less than. So all the pairs that I must get must follow that relation. That's why I see me have from the 1, 2, 3, 4, I have 1 less than 2. That's the first pair. 1 less than 3, that's the second pair. 1 less than 4, 2 less than 3, 2 less than 4, 3 less than 4. You follow me now? Those are the pairs that we can get from the less than relation.
Yes, sir, I get it now.
Okay, good.
Sir.
Uh-huh.
But is there any other way you can actually write the set? Get sets from set B?
Well, you could dumb them up. You do it in order. Yeah, man, you could use different relations and get different sets. If you were to just write the entire set B by B, then you will get 1, 1, 1, 2, 1, 3, 1, 4, then 2, 1, 2, 2, 2, 3, 2, 4. All the possible sets. Just repeat the numbers and put them, combine with each number, first and second. That will give you the entire set of B by B. However,
Right.
if you want a specific relation, no, it's limited to what relation requires.
Okay. So this capital R is basically saying you want all the unique sets that are subsets of B.
Yes. Yes. Whenever you get a subset from B, you're actually getting a relation. Just that you need to define what the relation is.
And these are unique. These are unique subsets.
Yeah, they are unique. If you leave out any element at all, you're getting a unique subset. The only subset that would not be unique is just the entire thing. But any other one is unique.
Okay.
All right.
All right. So
That was the relation.
Is there a particular question you could ask, and we would have to somehow write it like this that you have here?
Yes, man. I can ask one right now. All right. So you finish writing what's on the board or what you need to write?
I have that, yes, sir.
That's probably need. Come again?
Yes, sir.
Okay, I'm going to clear it. I'm going to put a different set. Let's say we have the set A, where the numbers are 3, 5, 7, 9. And I ask you to find the relation, using the relation greater than, where R is the relation greater than. What will be the subset of R? The sets of R, sorry.
I'll let you know. You just find all the.
Sir, so for that one,
sir,
for that one, would you say 5,3? Would you say 5, 3 instead of 3, 5?
That's correct.
Okay.
Because now you're saying 5 greater than 3, so you have to put the 5 first. If you put the 3, then 5, that you're saying that 3 is greater than 5. So keep going, give me some more. Hello? Anybody?
7, 5, 7, 3, 9, 7.
9, 7, yeah. I didn't hear the one. What you said one before. I didn't hear what you said before 9, 7.
7, 3.
Oh, 7, 3. Okay, that's correct. You finished?
9, 3, 9, 5.
Right. You see, if you don't do them in order, you might leave out some, you know. You got them though. 9, 3, 9, 5. Let me just double check now. 5, 3, 7, 3, 9, 3. We have that. 7, 5, 9, 5. Have that. 9, 7. Okay, yeah, that's it. All right, so this is not so hard. Some of the relations get more technical, but
it's not hard.
Not hard. Once you understand the general thing about relations and how the sets are formed and how to write them, then you're good. Sometimes it doesn't matter which one comes first. Like if I use the relation equal, well, there's only one that can come first, the same number. You could only write 3 equal 3, 5 sorry, you could only write this. If I use equal for the relation, I could have only written 3, 3, 5, 5, 7, 7, and 9, 9. You get the idea? So there are different relations that we can use. That's just, but normally, what you want, the purpose of this part was for you to know that equal, less than, greater than, less than or equal to, greater than or equal to, they're all relations in math. So it relates one side of the equation, if you want to call it that, or inequality, to the next side. Just that we didn't formally call it a relation. All right. So now here's the next definition.
My only thing with the equal now, you didn't really have A times A. So why would we have 3 times 3 when it's only one member we have in the set?
No, man, when you do a relation, you're relating one set to next set. In this case, I was just using, so all the sets that I did so far were the equal, the less than, and the greater than that what I just did a while ago. We're relating the set, we're using the Cartesian product for the set by itself.
Okay. But you didn't have to state it then. You could just leave it as just A equal whatever. You didn't have to put A.
Right. Because once you do a relation, it's one set to a next set. But so once the relation, and you see it's right. Okay.
So do you need
because I could have related A and B.
So like the A, that's what, A by B or A times B? How do we state that?
This was A by A.
A by A. Okay.
Yeah. Relating the set to itself.
Okay, gotcha.
All right. But that's a good question because sometimes you can relate A to B and use the same less than or equal to or greater than. So you could be relating what sets in what numbers in A are less than numbers in B. So you could have done it like that as well. But it would be mentioned to you if that's the case. You'd have seen A by B, so you would know that the A one must come first and the B one comes second.
Oh.
Kind of messy. Yeah, but you'll see. Don't worry about it.
Huh? When I say the A1 come first, what is the case when it's greater than and the elements in B might be smaller than the elements in A and you're using greater than? Wouldn't you put the B1 first?
No, empty set. Whenever you're relating whenever you have a Cartesian product and you put if I put, let's say X, I shouldn't use X because we have here X times, let's say Y by Z, you have to put the Y terms or Y values first.
Okay.
So it's like matrices.
So you're not just looking at the numbers that from both says which one is greater than the other in that case. You basically have to ensure that the Y elements are first.
Right. So the Y elements have to be greater than the Z elements to form the pair.
Okay. So you'll be looking for all the Y elements that are greater than the Z elements then.
Correct.
Okay.
That is right. Because remember, if you go back in the notes, look for the definition for Cartesian product. Yeah. You will see where I said, let me write it again so it's clear in the brain. If you have A by B, you're getting the set X, Y. And it was clearly defined that X must be from A and Y must be from B. So you see, it wasn't possible for the first element in that to be from B.
Okay.
It had to be from the A.
Right. Thanks for that reminder. I like that. Thank you, reminder. It's more clear now.
Okay, good. All right, so back to relation. What was I going to say again? I was going to define something. Define binary. Oh, need to define the reflexive, symmetric, and transitive business. All right, so write this down. Next, this is a definition now for, well, properties of relation. So let R be a relation on a set A. The same fancy R. Once you say relation is the fancy R. It's actually, see if I can draw it properly. It's actually something I have to draw. Oh, apparently I can't. No, something I did. Oh, forget that. All right. So let R be a relation on a set A. I have to take a picture and send to you. Or find it online and copy and paste. Full stop. So let R be a relation on a set A. Then R is said to be, we have three things. R is said to be 1, reflexive. R is said to be reflexive if A relates to A for all A in A. Can use element of this time. R is said to be reflexive if A relates to A for all A in A. So reflexive means, it relates to itself. But it can be just one or two elements. Every element has to relate to itself. That happens with equality. So equal is well, let me not say anything. I'm going to ask you later what you think is reflexive. That's part 1. R is said to be A, well, 1,
Oh,
reflexive. Sorry, what again?
Could you repeat the reflexive part? Like after you said it's said to be, it was breaking up
Reflexive.
and I couldn't hear.
Oh, okay, no problem.
Yes.
Then R is said to be 1, reflexive. So you should write the word reflexive. If, see if I can squeeze in everything. If A relates to A for all, use a symbol because I can't squeeze in the words right there. For all A in A. That's what I said. If A relates to A for all A in A. Right. For number 2, symmetric. Symmetric. If A relates to B, implies that B relates to A. I'm using shorthand here, but you can write the words. So it's symmetric if A relates to B, implies that B relates to A. And the third word already, all of you that did college geometry. What's the modern algebra? I don't think so. Transitive. Transitive. Oops. Transitive. Does anybody remember what transitive means? No? All right. Transitive if A relates, I don't remember. All right. Here's transitive means A relates to B. Sorry. It's transitive if A relates to B and B relates to C. I can pick it up now a bit. Implies what? So if A relates to B and B relates to C.
A relates
then,
to C.
Correct. I knew you remembered it, man. A relates to C. So it's transitive if something from A relating to B and something from B relating to C means that the A relates to C.
We're gonna get example of those, right?
Yeah, man, an example of all of them.
Okay, all right, good.
So have that now. Now, here's one more thing to note though. If R is reflexive, symmetric, and transitive, if R relation is reflexive, symmetric, and transitive. Oh geez, forgot about this one. No. So if R is reflexive, symmetric, and transitive, then it is said to be an equivalence relation. If R is reflexive, symmetric, and transitive, then it is said to be an equivalence relation. You know, I didn't write this because people have spelled this wrong before, so let me write it. It's an X, not reflective, reflexive. There are certain things I will take off marks for. That should be common knowledge.
So can you have an equal relation as well?
Yes, man. No matter if that's the first example I'm going to use.
Huh?
That's the first example I'm going to use to show reflexive.
Okay.
Sir, what was the last word you said?
Transitive. Oh, equivalence.
No.
Equivalent.
Equivalent.
Wait, which one is that? Yeah, equivalence. Equivalence relation. Those are E's. I don't know why E's look so weird. Equiv, L-E-N-C-E. Let's see if I write it. Common letters, if you can see better. Oops, that's better wrong. Oh, is that you? Right. Equivalence. Mhm. Wait, give me a minute.
Yes, sir.
Yeah, sorry about that, guys. All right, you had any other questions? Hello? No
Yes,
questions?
sir.
All right.
No.
Okay, good. So let me show you an example of reflexive now. Let's say we're using the reflexive relation here. So remember, for it to be reflexive, the set has to reflect to itself. I mean, it has to each, or by the way, let me go back to the top. For a relation to be, I want to find the exact words that I use so you can know that it is inclusive of everything. I'm not seeing, where did I mention? I didn't mention it. Oh, yes, right at the start, definition, right at the start of the definition, it said, let R be a relation on a set A, right? Then R is said to be reflexive if A relates to A for all A in A. Now look at this. Suppose my A was, let's say, 1 and 2. Not for argument's sake, 1 and 2. And I was going to relate A to A. So you know that you're going to get the set A by A. So from let me write all elements of this set. Oh, let's say the relation that we're using is equal. Let's say that's the relation, equal. In A, you get 1, 1. If A by A, you're getting 1, 1. You're getting 1, 2, 2, 1, and 2, 2. Now the only elements from, or the only elements from that set, because this is set we're getting now, from A by A, this is A by A. A by A would be this. The only elements that would fit the equal would be this one and that one. So as you can see here, the equal relation would not be reflexive because it's supposed to be A relates to A for all A in A. But that doesn't occur in this case. But look at this now. Suppose I was going to use a different set. And say the set is B, which is equal to just the number 4. That's the only element in the set. So we want to get these relations now, are these Cartesian products, B by B, which is just simply 4, 4. In this case, if we're using the equal, a matter of fact, if you use even less than or equal to, every element in B can relate to every element in the next B, because 4 is equal to 4, and that's the only element you could equate to itself right here. It doesn't work in 1 before because 1 is not equal to 2, 2 is not equal to 1. And for it to be a reflexive relation, every element, every A by A must, A must relate to A for all A in A. My mistake. What was I saying a while ago? Oh, wait. I'm using the wrong thing here. Whoops. Hold up. Let me start again. I made a little mistake right here. A good thing I check it back in. I was thinking about the wrong I was thinking about product rather than relation. Beg pardon. 1 relates to 1, 2 relates to 2, and 3 relates to 3. It still comes from A by A though, because if I get it from A and get it from A. But for it to be reflexive, the element must relate to itself. I made a mistake a while ago. I was looking at all the possible elements of the cross product, the Cartesian product, but that's not what is required for reflexive. For a set to be reflexive, every element in there must relate to itself. So if we're using the equal relation, if the relation is equal, relation is equal, then every element would be reflexive, would relate to itself, because every element is equal to itself. So the relation equality would cause a reflexive relation right here, because 1 is equal to 1, 2 is equal to 2, 3 is equal to 3. That's an example of reflexive.
Okay.
Like I was saying before.
All right.
I was using two different.
So you're saying that. So you're saying that using. So we're scrapping what we looked at before, and you're saying that if you're looking at A by A, and they're asking for a relation that is equal.
Yeah.
We still can get an equal relation by simply using the elements that are the same.
Yes, because that's to be the same. Because you notice the reflexive was A must relate to the same A.
Right. Okay. So even though in both A set A and itself, even though you can have one and 2, as when you're looking at the subset, you just basically leave those out.
Right. You just look at the similar ones that are like.
Are equal. Okay.
So for it to be reflexive or equal, if you want to say that, then it must be related to the same element.
Okay. So that means if we have set A by set B, then similar to the example you're using before, that means you wouldn't need just 4 alone in that case. Then you could have several other numbers as well, and you just relate those that are equal.
Correct.
Okay. So if you have B equals 2, 3, 5, you can still put 2 relates to 2, 3 relates to 3.
Right. 5 relates to 5.
Yeah, and that would be about it.
That's right. Oh, you mean if you had 2, 3, 5 along with this A?
If it was an A by B and you had B equals the set of elements
2,
3,
3, 5.
and 5. Yeah.
Yes, those are for the equal ones, right? So you relate 2 and 3 and 2, 2.
2 and 3. 2,
just
2 and 3 will be.
Okay. Just the ones that are the same.
Okay.
Yeah. All right. So that's an example of reflexive. If each element relates to itself. Let's look at symmetric now.
You said each element relates to itself, but it wouldn't be a case where all elements need to be related to itself.
Yes, because it said for all A in A. All the elements that are the same have to relate to themselves.
Okay.
Right.
All right.
It won't work unless it works for all of them that are like.
Okay. I'm just looking at the terminology for some reason. It seemed to be saying all the elements have to be related to themselves in a sense. Like you can't have
that's what it said.
You can't have any in there that would not be able to relate to itself.
Correct. That's what it said.
It just more seems as if what you were saying before is correct compared to what you have here.
What I was saying before is more correct than this. Look here.
From the definition.
All right. Look at this. Look at this. Let's say I have a completely different set, C, and this set contains all the numbers from 2, 4, all even numbers, 6, all the possible even numbers you can think of, right up to wherever. For the relation to be reflexive, every element in that set must relate to itself. And if you were to put 2 sets like what you said a while ago, once the elements are alike, which obviously just means it's the same number, they must relate to themselves as well. So it doesn't matter how you want to look at it. The elements must relate to themselves. Once they're alike. So of course, if they're alike, then I mean, if they are themselves, then they must be alike. It must relate to itself. That's what it's saying.
But
and it's not just equality that works for.
So right, but you wouldn't consider that the whole both sets themselves are reflexive. You wouldn't say that the both sets are reflective.
No, that won't happen. You can't say every element in both sets are reflexive because if you remember, you have to look for only elements that are alike. Because if you're going to use A relate to A, you can't use a in C and then a B in B and say A relate to B. It has to be the same element.
Right.
Yeah.
So can you say that in this case, could you say, like, for example, you have A and C there? You can say set A is and C are reflexive? You can use those terms?
No. You won't be able to say, because I think I'm able to say, I think what you're doing is confusing Cartesian product with relation.
Okay.
If you look back at the first thing that you were told, it must be a relation on a specific set. Look right back at the start. Let R be a relation on a set A. As I was telling you what I was saying before would confuse you, you know.
Yeah.
I was looking at the product rather than the relation.
Okay.
That's why I said scrap what I was saying before.
All right.
Yeah.
It just made
Sorry
sense.
about that.
No, man, it made sense. That's why I can't hold on to it. But I'll let it go. All right.
All right, good. All right, so symmetric now, example of that. So A relates to B implies that B relates to A. So for A to be related to B, remember that the A and the B are in the same set A, you know. Hold on. A relates to B means that B must relate to A. So once again, oops, come on A. So remember the set. I'm going to use the equal for this as well, because you know it's easy to just use equal for all of them, because equal is actually equivalence relation. So I'm just going to be lazy and just use equal. So let's say you have a set A, which is 1, 3, 5. Then if 1 is equal to 1, and as you write in the words, it means that 1 must be equal to 1. So A, not A, beg pardon, 1 relating to 1 is symmetric, because it doesn't matter how you turn it around, it implies that the other way around is the same thing. So once you can flip the thing and it still relates, then it's a symmetric relation. If I can think of an example quickly that works. Because this one kind of hard to.
Sir, that be the case. Does that mean that symmetric and reflective is the same thing?
No. All right, let me find a different example because I don't really think it's the same thing. What can I use? Let me scan through quickly and see if I can find any relations in it. See if I have an example here. Symmetric is hard to find, you know. Easier to find the other two. Symmetry. I tell you what, I'll come back to it. I was going to go to the next one because I forgot to scan online for that. Symmetric relations. I know I can do it with triangles, but I want it to be numbers. All right, come, soon come. But that's a good question, though, but it's not the same. It's in this case, because it's the same number, it looks like the same thing, but not necessarily the same. What symmetry means, you know, is that if A, some number, is related to B, then if you flip it around, that same number must be related to A for it to be symmetric. But when you're doing reflexive, it must be the same number. It must be A and A. Like if you're using the relation less than is not reflexive. Because if I say, you cannot say that 4 is less than 4. So the relation less than is not reflexive. It's not symmetric either. Because we know that 4 is less than 5, but 5 is not less than 4. So it's not symmetric. So for it to be symmetric, it must mean that sometimes it might appear symmetric, you know, if you get tricked. Like look at this. 4 is less than or equal to 4. And flip it around. Let's assume we flip it around by doing it this way. It would still look like 4 is less than or equal to 4. But that's not, it just works one case like this. But if I were to use a different number, like say 4 less than or equal to 5, it will not work when you flip it. Actually, flip it around in the first one, you know. Lord of mercy. 4 is supposed to be over here. Hold on. I don't want to confuse it again. So, all right, tell what I'll do. I'll write it in different letters, different colors. 4 is less than or equal to 4. If we were to flip it, 4 is the same 4 that's written on different sides. It looks like, so this is actually looking like a symmetric relation. Okay, so the same number goes on different sides. But if I were to, actually looking reflexive. But if I were to use a different number, 4 less than or equal to, less than or equal to 5. And I were to flip them around now and say 5 less than or equal to 4. You will say that is not symmetric. Because even though you flip it before and the relation seemed to be symmetric, when you use two different numbers now, it's not symmetric anymore. So for symmetry, you need to use, it's best to use two different numbers. But for reflexive, it has to be the same number. So that's why I'm saying reflexive and symmetric are not the same. So for reflexive, it has to be the same number. Let's say 4 and 4, 5 and 5, -1, -1. But for symmetry, it must work for two different numbers. Meaning that if I tell that this number A relates to that number B, it must mean that you can write it this way as well. B relates to A for it to be symmetric. You have to be able to put on sides. Like what we tried right here, which didn't work. It didn't work on both sides. So it's not symmetric. Less than or equal to is not symmetric. So as I said before, I'm going to find an example quickly. Well, not quickly, but after we finish transitive, I'm going to find an example where you can see that the relation is actually symmetric. It shouldn't take me long, maybe 1 minute to find it when I finish the transitive. All right, so let me show you an example of transitive now. Everything will come off the board. Yeah, transitive. So for transitive, you know, if A relates to B and B relates to C, relates to C, it is telling us that A relates to C, which is the case with less than, because if 1 is less than 2 and 2 is less than 4, then it means that 1 must be less than, I should actually write less than, you know, less than 4. The relation I'm looking at right here is less than. I said it, but I didn't really write it. So we're looking at less than. Less than is actually transitive, because if one number is less than the next number, and that other number is less than the next number, then it means that the first one must be less than the last one. As I see on the board here, 1 is less than 2, and 2 is less than 4. So it means that 1 must be less than 4. Less than. So less than is transitive, but it is not symmetric and it is not reflexive. Equal is reflexive, but it's not, well, equal is all of them. Because if you were to use equal, let me write it a different way. If 1 is equal, no, use 4. 4 is equal to 2 plus 2. I'm using different numbers here, it looks more, you know, more sensible. And 2 plus 2 is equal to 3 plus 1. So that implies that 4 must be equal to 3 plus 1. I'll just split them so it looks more fancy with the transitive business. But actually it's the same number. 4 is equal to 4 implies that 4 is equal to 4, which means that 4 must be equal to 4. Equal is an equivalence relation because it fits transitive, reflexive, and symmetric. transitive also applies to less than. It applies to greater than. It applies to less than or equal to. It applies to greater than or equal to. All of those relations are transitive. Because it doesn't matter out if one number is less than or equal to the next number, and then the other number is less than or equal to a further other number, then it means that the first number was less than or equal to the last number. So less than or equal to is transitive. All right, so think about your questions while I try to find an example for symmetric, a different example than equal. If you have any questions, that is. Symmetric examples in math. All right, I want numbers, not this. Oh, this is the equations thing. I suppose I can have sets with equations, yes. Why didn't I think of this? All right, here's the next example of oh, that's the next example, the same example. I was going to use this. I was going to use if x, I saw this one a while ago. If x plus a, well, I think they had y, but anyway, if x plus a is equal to 7, then 7 is equal to x plus a. Which is the same equal thing though, but I wanted a different one. Honestly, there's something apart from equal that is symmetric. Yeah. Oh well, we'll come across it in exam, in questions. I'm going to do some questions when I get to the end. Haven't checked the chapter yet. There might be some questions there that have it. Well, let's jump to it. Questions. Oh, that's not symmetry. That is less than. That is blah, blah, blah. Okay, there are no questions.
So,
yeah.
I am seeing a definition online, but I don't know if that could work as well for symmetric relationship.
Well, we're doing symmetry in terms of real numbers, but go ahead.
Okay.
Let me see if it applies.
All right. It's saying there that if you have if open bracket a comma b close bracket are in set R.
Yeah.
All right. And it implies that with a straight line, that b comma a, that's in a set form, are members of R for every a comma b in A. For every a comma b in A. And then there's an example where it says let a equals 1, 2, 3.
Well, but it's the same thing we had before. They just wrote it a different way. You see what they have right here, the a comma b in R, it means this. A relates to R. I mean relates to B.
Right.
Saying B relates to A.
And they have this example. So it has like this as an example now. Let a equals 1, 2, 3.
I mean capital A.
Yes. Let's set A, sorry. Let's set a equals 1, 2, 3. And R be a relation in set A given by R equal.
Given by R equal what?
The set notation, set open bracket, the set symbol. R equal the set of elements 1, 1.
Or they're using the same equal. Maybe equal is the only one then.
1, 2.
They have 2, 2, 3, 3.
1, 2. And then 2,
they have 1, 2?
Yes,
hold on. This is interesting now. All right, hold on. Let me hear that. A is 1, 2, 3.
Yes, sir.
And R is 1, 1. You said 1, 2 as well?
Yeah, 1, 2. 2, 2.
Yeah.
And 2, 1.
2, 1. All right. Oops. 2.
And then it says then R is a symmetric relation.
Oh yes, it is, because 2, 1 is also in a set and 1, 2 is in a set. This is a good example. Thank you, Anthony. That's a
But
actually I've created this as R. I didn't think of that in.
well,
Hmm?
I don't know if it's accurate because I just
It
saw
is,
it
it is,
online.
it is. And the reason it's accurate is because they didn't tell us what the relation is, you know. But they said that in that relation, the set created is 1, 1, 1, 2, 2, 2, 2, 1. The reason it's accurate is because for every element in the set, all right, let's look at the first one. You see 1, 1. It doesn't matter how you turn it around, 1 is still related to 1. So that one is set. For 1, 2, no, for it to continue to be a relation, no. Once you can write this, 1 related to 2, you should be able to spin it around as well. And you can see 1 related to 2, but 2 also relates to 1.
Right.
Yeah, so it fits it.
Okay.
Because from once you have a certain A related to B, you should be able to spin it around and get B related to A, and they put both of them there. So if they were going to put in this set a 3, 2, then they would have to also have a 2, 3.
Okay, I got you.
Yeah.
But okay.
So they haven't defined a relation in terms of an equal or some operation. They just actually created the set.
Yeah, they created the R.
That's the info. Right.
But
Hmm?
does that make it harder though? Because so they would have to create
No.
the R then.
Yeah. That's an example I didn't find out. I'm glad you found that one. Because if I'd seen it, I'd have used it. Maybe I typed in the wrong thing. But it's a very good example. Thanks for that. Because the relation doesn't have to be defined by the operation or some equal or less than. It can just actually be the set. So those are the relations coming from R. All right, so thank you for that. All right, so we have 20 minutes. Let me finish this part. So now the definition. So that's a definition, guys, of symmetry. This relation right here. So we have this set, and from that set we have the relation defined right here. So you guys can use that one from Anthony. Okay. So as I said before, equal is reflexive. That relation there that we just got is symmetric, and equal is also symmetric. Transitive now, all of them that we're used to, equal, less than or equal to, greater than or equal to, all of those are transitive. But they are neither, the ones down here, the bottom ones, they are not reflexive nor symmetric. But they're all transitive, along with the equal. The only one from all of these 5 that is an equivalence relation is equal. But I can actually create a set as well that fits all 3 criteria. So I can do that later. All we have to do is just put everything in there. What if I let me create one? So you can say it is met. So as I said before, just to reiterate, equal is an equivalence relation. Less than, greater than or equal to, less than or equal to are all transitive relations. Make sure I write here, transitive. They are not symmetric and they are not reflexive, but they're all transitive. But everything now combined with equal is transitive. And the equal is also reflexive and symmetric. So it's an equivalence relation. And this one right up here in the box is an example of symmetry. Yeah.
Say it again. Reflective is what? What are the signs for reflective?
Reflexive, equal is reflexive. Is an effect. Equal is a reflexive relation. Or the relation equal is reflexive.
And what is symmetric?
Equal as well. And the example we have on the board, that relation is symmetrical.
And the others are transitive.
Right. All of those are transitive.
Okay.
The less than, greater than, and whatever. Those are transitive.
So I see an example where they actually put in the same another definition, but they actually put in just what you have there, the 3, 2, and 2, 3. So they're saying
to
like
get symmetric.
Yeah, to make it symmetric.
Yeah. Because once you can turn it around, man, then it fits it.
Yeah. So 3, 2, and 2, 3 can be entered as well.
And if you were to
And
put
then
an x4, if you were to put the number 4, you could also have 2, 4, 4, 2, 1, 4,
Right.
2, 4, 1.
right.
If any of them is missing, then it's not transitive, not symmetry. If you
Okay.
had put in the 3, 2 and not put in the 2, 3, it would not be symmetric.
Okay, so it's as long as you can create that relationship as a set where you have them A comma B is equal to B comma A.
Yes. But I prefer when you say A, R, B, B, R, A, you know. Not really
Okay,
equal.
all right,
Yeah.
all right. Then
Once
you're
you can
right,
flip
you're
them.
right. Yes, yes.
Okay. All right. Next definition. So I can finish the definitions right here. We'll just have 2 more, I think. 1, 2. Yeah. Time, man. Okay. So let A be a set. So this is the definition now. Let A, it's a definition of equivalence class, if you want to write what it is. Equivalence with a C, class. Sorry. All right, so let A be a set and R, let A be a set and capital R, an equivalence relation. Oh, so Anthony, you see the R online. You see what the R looks like. I'm not able to write it on the board. My skills are not that good.
Oh, they just wrote it like the regular capital R.
Eh? Oh, it's normally fancy anyway.
It's typed.
All right. So let A be a relation, sorry, let A be a set and R an equivalence relation. So remember, if it's an equivalence relation, you know, it must mean it's symmetric, transitive, and reflexive. Good. Full stop. An equivalence class is what we're defining now. An equivalence class of A in A, an equivalence class of A in A, denoted by this little A in a box right here. That's an equivalence class of A. An equivalence class of A in A, denoted by the symbol here, close brackets around A, is the set, this is the set, X in A, such that A relates to X. Let me give you an example of this one now, so you understand what is being said right here. All right, let us say we have, so you should have this already. Let me just repeat it. Let A be a set and R an equivalence relation. An equivalence class of A, element of A, denoted by a close bracket around A, is the set X in A such that A relates to X. In other words, it's all the X's in A that relate to A, or that A relates to. All right, so here's a quick example. Let's say we have the set A again, 1, 2, 3. The set A, let's say it contains 1, 2, and 3. And let's create a relation like we did last time, but like Anthony did. And our relation contains 1, 1, 1, 2, 2, 1, 2, 2. But let's also include one more, 3, 3. All right. That's an equivalence relation. So before I even go to the equivalence class business with the A, let's first show you that it's an equivalence relation. You notice that for it to be an equivalence relation, first of all, every element must relate to itself. Is that being shown here? Let's check. 1 relates to 1, so it's reflexive. 2 relates to 2, and 3 relates to 3. All of them related to themselves. So they are reflexive so far. So far, R is a reflexive relation. Why? Because every element in A related to itself. That's the key thing for it to be an equivalence relation, you know. Sorry, for it to be reflexive. Not the key thing, that is the thing. For a relation to be reflexive, every element in a set, A, 1, 2, and 3, must relate to itself. See, 1 is relating to 1 right here, underlined. 2 is relating to 2, 3 is relating to 3. So far we see that it is reflexive. For it to be symmetric, if you have one element relating to our next element, it must also be, the flip must also be true. Let's check that. See, here we have 1 relating to 2, but therefore 2 must relate to 1. So you see it's reflexive so far. I mean symmetric, beg pardon. We didn't have 2 and 3, so we didn't have to check for 3 and 2. Nor did we have 1 and 3, so we don't have to check for 3 and 1. But once an element relates to our next element, the converse must also be true. You should be able to flip it and see that in the set as well. If they have 1, 2 in there and they don't have 2, 1, it would not be reflexive. Lord have mercy, sorry. It would not be symmetric. I keep mixing up those words in there. Reflexive is the element in itself. So symmetry now. For it to be symmetric, if one element relates to our next element, the converse must also be true. You must be able to flip it and see the same thing happening. So since we have 1 and 2, we should have 2, 1. If we also had 1 and 3, we would have to have 3, 1. If none of them are there, it's fine. You don't have to check for the next one. But if one of them is there, the reverse must also be there. So
Okay.
this relation is reflexive so far, and also symmetric, because both criteria are met. Now for, what I think name again, transitive. For transitive, you know, here's what we should be looking for. I'm right here quickly. A relating to B, and B relating to C, oops, relating, not C, relating to C, must imply you must be able to find A relating to C.
Okay.
You see any evidence of that in this set? Any evidence of transitivity?
Unrelated to 3, unrelated to.
Right. It's a bit tricky to find any, but you can find one right here. Let me circle them or use a different color. Let me use it's kind of not as obvious because it's kind of not fully 3 different elements. But look at this.
Yeah, I see one, sir.
What is that?
If you look at a, it's one relation. No, I don't see it. I don't see it. I don't see it. I don't see
I
it.
don't see it.
Because you have to bring
All right.
a third of it, which.
Right. You need a third one to see it clearly, which is not the case here.
No.
All right. But do you see any evidence of it going against transitivity?
Go against transitivity.
Meaning that you see like something related to something and then the converse wasn't true. Meaning like, let me show you what I was talking about. Right here we have 1 relating to 1. The first one, I'm underlining them as I go along. So far we have 1 relates to 1. And if we go to the next line, which is now this, 1 relates to 2. So what should be the final step?
2
Use the A
relates
and the
to.
C. No,
Well, 1
Related to
relates.
some
1.
people think 1 relates to 2. Good. That's the best we can get from that. We could also have used,
But you have one. What would you want to put? 1 relates to 1 as A relates to B, given that they're 2 different numbers. It's the same number.
the same number. All right. If you want to get more technical, look at this then. Look at this one. Look at this one. 1 relates to 2. That's 2 different numbers, right?
Yeah.
1 relates to 2. Next one is 2 relates to 1. Do you see any set that says 1 relates to 1?
Okay.
An elementary. That was the one I was pointing to initially.
But
I think I
sir,
wanted to find at least 3.
I am still thinking that if you have 1 relates to 2, then 2
Yeah.
relates to 1 should really be B relates to A.
Yes, but look here. Let me make sure you're clear on something. If this was not here, it would not be transitive. If the 1 was not there, it would not be transitive. Because if 1 relates to 2 and 2 relates to 1, you have to have 1 relates to 1. So if that 1 relates to 1 was not there, it would not be transitive. You follow me? Because we have 1 and 2, We have 1 related to 2, 1, 2, the second element right there. After 1, 1, we have 2 related to 1. So you had to have 1 related to 1. So it might seem simple, but if the 1 related to 1 was not there, it would not be transitive.
But what I was saying though is that if we have 1 relates to 2 and 2 relates to 1, so shouldn't 2 relate to 1 be really B relates to A and not B relates to C?
Yeah, but it's still a different element. Even though it's not exact 3 different elements that you saw. Look here. When you see them put A, B, A related to B, B related to C, and A related to C, it doesn't necessarily have to be 3 different numbers, As you can see right here. It doesn't have to be. It just has to be A and B are different, B and C are different. But A and C could be the same, B and C could be the same. No, B and C different. But A and C didn't have to be 2 different numbers, as you can see right
Okay.
here. As long as you had 2 different solutions, A, B, B, C. But just to be clear, because you might overlook that, you might say, okay, we can't find any in this, but in this case right here, if that 1 was not there, it would not be a transitive set.
All right, so A and B and B and C and so forth. That's just relate. That's just talking about 2 different elements, really. So if you have an element relate to another element, and you also have its reverse as well, then the first one and the last of the last one should be there.
Right. Correct. That's right. Jermaine, were you asking something? I heard your voice before.
Sorry, I was making the point that I saw that those are the first 3 are transitive.
Oh, the same thing I just showed.
Yes, sir.
Right. Well, that's good. I picked it up, man. All right. What was I going to show you a while ago? Oh, we haven't even started. We haven't even done what I wanted to show you. The first of all, I wanted you to see that was an equivalent relation because it satisfied all 3. Yeah.
So, what in a case where we have like 2, 2, and 3, 3, shouldn't we say if 2 relates to 2 and 3 relates to 3?
Then what?
Are we saying that those B's have to be the same?
Yeah. Oh, you mean talking about the same transitive thing?
Yeah.
Yes, man, the B's have to be the same. You have to follow. Like, whatever you end with, you have to start with it next time.
Okay.
So if you go 2 related to 2, then you have to go 2 related to something else.
Okay.
You can't go to 3 after that. Yeah.
So, sir, if you say 2 relate to 2 and 2 relate to 1.
Good. Hold on, write that
So,
down. If you say 2 related to 2, 2, and then 2 related to 1, that's good so far. So watch the had in the end.
2 relate to 1.
Yeah, that's it. Which is
1
there.
relate to 2.
That was similar to the one I had up here.
Yeah.
But this one was a bit more.
Okay. So I have a question.
What we wanted. Now go ahead, because I'm gonna show you the equivalence last time.
No, for reflexive, as long as you have AA in the relationship, it doesn't matter about the others. Is that the case? It would be in a.
As long as you have reflexive.
As long as you have AA, as in A comma A, for example, or A.
Yeah. Then what do you mean doesn't matter about the others?
As in, if you have, okay, let's look at this one, the R relationship. It's reflexive because we have AA, as in 1, 1, 2, 2,
3, 3.
and 3, 3.
Right.
But we also have 1, 2, which is not A comma A, ARA. Let me put it
I'm
like
not
that.
sure you're asking. You're talking about reflexive specifically. As
Yes,
long as you
reflexive.
have 1, 1, 2, 2, 3, 3. Yes, that's the
Right.
case. You
But
don't
you
care
have
about the
to
rest.
have, but you one one two one and two one shouldn't be in there then.
1, 2, 1, 2, 1 should not be in there. For
I'm
reflexive, no, we don't need it for the, no, that's not required for reflexive.
But if it's in it, can we say the whole set is still reflexive?
Yes, man, look here. Let me make sure you understand what reflexive means, or is what is required for reflexive. For a set to be, for a relation to be reflexive, everything that was in the previous set. So if, look here, if let's say in the set we had 1, 2, 3, and 4, this would not be a reflexive relation because the 4, 4 is missing. If that relation is the set we're using
Okay.
to show the equivalence.
As
For it
long
to be an,
as long as okay, I get you now. I got you.
you need to
So
have all 4 of them.
what set you create, just ensure all the reflexive ones are there.
Yes, everyone has to be there. So if
Right.
1, 1
As
was missing,
one,
or 2, 2 was missing, or 3, 3 was missing from the A,
yeah, yeah.
then it would not be reflexive.
Okay. I was thinking that it should only contain 1, 1, 2, 2, 3, 3, and 4. But now I'm understanding that it would also it doesn't matter what else it includes as long as it includes 1, 1, 2, 2, 3, 3, and
Right.
4.
As long as it includes the doubles, then you're good.
So even in this like the example that we use 1, 2, and 3. Let's say we didn't include 2, 1, but we include 1 or 2. It will still be reflexive because we included
Right.
the 1, 1, the 2, 2, and the 3, 3.
That's right.
Okay.
Good. So the
You
other,
just have to have the requirement.
whatever additional thing is included doesn't affect reflexive.
Right. You just
As
need
long
to
as
have the
what?
requirements.
Good, good. That's it. All right. Now for the a few minutes left. So for the equivalence class, let's say we're using. All right. The equivalence classes will be this. Remember, for an equivalence class, let's say look back at the definition. So if A is a set and R is an equivalence relation, like we have right here. Let me just clear this back and write it quickly. I don't want any confusion. So the A was 1, 2, 3, and the relation was 1, 1, 1, 2, blah, blah, blah. 1, 1, 1. Of course, you don't have to put them in order, So I'm going to put it like this. It's a set, so it doesn't matter how you write them, as long as you have all the required elements. Oops, I was going to put 1, 2 first. It doesn't matter. 1, 2 here. I think that's what we had a while ago. Yeah. So remember, an equivalence class of an element is the set X from that previous set A, which has A relating to X. So let's say we want an equivalence class of 1. What elements relate to 1?
1 and 2.
2. Good. So we have 2 relating to the 1. So the equivalence class of 1 will be the same as the equivalence class of 2. Why is that? Because everything that relates to 2 relates to 1 as well. You see that?
Oh, okay.
So that equivalence class is simply the set containing 1 and 2. What's the equivalence class of 3? So if you were to actually write this properly, I just do it in shorthand and write 1. The equivalence class is actually the set at the end right there. 1 and 2. I'm just lazy and put 1 equal 2, but it should have actually been 1. Equivalence class of 1 is 1, 2. The equivalence class of 2 is also 1, 2. But the equivalence class of 3 is what? What's it?
Okay, just 3 alone.
That's a set 3. So just to make sure everybody is clear, right here, let me put a little red line below it. This is square brackets. This is also square brackets. I was just lazy a while ago and put 1 and 2 in the same line, but that 2 right here on the line right there is just really this one. I'm just showing that this is the same equivalence class, both of them, 1 and 2. Because remember, the equivalence class is a set containing the elements from A that related to that element. So the equivalence class of 1 would have been the set of elements that related to 1. If you look up here, 1 related to 1 and 2 related to 1. So all elements that related, sorry, all elements that your element related to. So I should have put is actually this one. Beg pardon. So you see the one related to 1 right here and one related to 2. Ones I'm underlining. One related to 1, one related to 2. So the equivalence class is 1 and 2. For the equivalence class of 2, I'm going to use a different color. Use blue. 2 related to 2 and 2 related to 1. So the equivalence class of 2 was just 1 and 2 because 2 related to 2, 2 related to 1. For the equivalence class of 3, 3 only related to 3. As you can see, I don't have to underline it. But what is the criteria for an equivalence class? For you to have an equivalence class, you must have a what? 2 words. For you to be able to have an equivalence class, you must have had an equivalence what?
Relation.
Feel bad, no? Correct, relation. You can't have a relation that's not an equivalence relation and then get an equivalence class. To get an equivalence relation, the relation must have been an equivalence. Sorry, my bad. To get an equivalence class, you could not have had a relation that was not an equivalence relation. So equivalence classes only come from equivalence relations. It's a definition. Let A be a set and let R be an equivalence relation. I can trick with questions like that, that's why I'm stressing these things. I could ask a question, what's the equivalence relation of that class? Sorry, what's the equivalence class of that relation? When there's actually no equivalence class, because it was not an equivalence relation. So I want those definitions to be stuck in your brain so you don't get tricked.
All right.
I'm not saying that I like to trick people, but I will trick you. Yeah, go ahead.
Yeah. When you say there's no equivalent relation, you're not referring to that you have on the board. You're just making a.
No, not on the board, not on the board here. This one is equivalence relation.
All right.
But I could actually give you a set and give you a relation, which was not necessarily a equivalence relation, and then ask you to find the equivalence class, which would not be possible. So the answer would have been there's no solution, there's no equivalence class, because it was not an equivalence relation. Follow me?
So once there's an equivalent relation, there is an equivalent class.
Yes, man, there will be. Has to be. Even if it's just the one element in there, like the 3 right there, but there will be an equivalence class for each class. For each element, sorry. Will be. There will be one. And that's because of the symmetry. You have to have one that goes both ways.
So
Right?
so when you have when you have reflexive, symmetric, and transitive in for a relation,
Yeah.
then it's equivalent. Question.
Yes, it's an equivalence relation. Once you have all 3.
So you must have all 3.
Correct. So think of any other questions. I'm going to stop recording here.